at 90 gives me less bang for my buck than getting from 80 to 90 gives me less bang for my buck than getting from 70 to 80 in terms of where I get into. That at some point, increasing everything overall reduces my, my return. And you usually justify this notion not because things are necessarily like that, but in the context of a market where there's a particular price, if firms don't have declining marginal product, they're going to choose never to operate in that part of their production function. Because if you have a linear price, you'd never want to produce at a point where you have increasing marginal product. You'd either produce above or below that point. And we'll talk more about that in the next lecture. Yeah, go ahead, Jacob.
So when you say bang for your buck, do we mean that what you spent, your cost of getting to 90-70 was higher than 80-80? Or that your score? That
your score increases more going from, you know, basically, if you increase by 10% and then increase by 10% again, you get less the second time than you did the first time. Yeah, go ahead.
But I mean, like I understand that like a concept, but like if you look at colleges, I mean the difference between like getting in here might not be that different from like a state school.
Yeah.
But you know, the difference in our scores might only be like that extra 10%.
Yeah.
So.
Yeah, no, that's a good point. So not everything necessarily satisfies that. These are the assumptions that we usually make. In fact, I chose this example because it showed you, it sort of gives you a sense of exactly the limitations of the assumptions we usually make, I think. This, I think, is really justified by, in a market context, if you're receiving a constant price for something, you'll never choose to operate at a point where you have increasing returns. So, but it's not, there's nothing necessarily true about that. The fourth thing we assume, which is actually pretty innocuous, is that things are smooth. Now, notice that this actually does go against some of the things we were talking about before. So the min function is not smooth, and the max function is not smooth. But both of them can be approximated by smooth functions. So we can take something which, rather than literally being kinked here, is just very, very concave, and that'll still work out. This basically is just a technical assumption that lets us use calculus to do everything. OK. Now, the most common function, which is sort of like a classic function satisfying all these assumptions, and I think going through these assumptions gives you a sense of sort of what is going on with this function, is the Cobb-Douglas production function. This says that the output is equal to some number times x to some power times a to some power. OK, so some of the properties that this has is it has constant elasticity of production. That is, if you have a p% increase in x, you get a, that thing's called Psi times p% increase in output. Is J min here? No? Is anyone else interested in trying to prove this? Either verbally or on the board? Jacob, yeah.
Well, it's sort of like placing weight on a certain input. So Cobb-Douglas allows us to look at specific percent increase in a specific input and have really nice outcome in production.
But so, can you prove from that form that what I said is true? That if you have a p% increase in x, that you get psi times p% increase in output?
Not mathematically.
Can anyone try to do that? Go ahead, Connor.
Should I do it on the board?
Yeah, whatever you want to do. Or you can do it verbally if you can do it verbally, whatever you want to do.
Okay, well, verbally, I think you would just, so isn't the formula for it just the new amount of production minus the old amount of production divided by the change in x?
Yeah, that's
so
right.
then you would just substitute, you do 1 plus p times x, you would substitute in that equation. For the, so it would be k times 1 plus p to the xi times a to the alpha.
Yeah.
And then minus just normal f of xa.
Yeah.
Divided by 1 plus p minus, or x, 1 plus p x minus x, and then there would just be px. And then I think if you simplify it, then you would get that.
Well, so that can work out. It only works out as you take the limit as p goes to 0. But I think the simplest way to think about it is that if you take the logarithm of that up there, right, you're going to get log of k plus psi times log of x plus alpha times log of a, right? And then you immediately see that if you multiply x by p%, right, that raises its logarithm by a certain amount, and then how much it raises its logarithm gets multiplied by psi, and that is how much the logarithm of the output rises, right? Okay. Second thing is that the function is homogeneous of degree psi plus alpha. So first of all, can someone tell me what homogeneous means of degree something? Connor, you want to go? Or no? Go ahead. Sorry, remind me of your name?
Matthew.
Matthew. Yeah.
So let's say, so if it was like homogeneous of degree 0, if you doubled the inputs in the function, then it wouldn't change the
output
at all.
Yeah.
If it was homogeneous of degree 1, then it would double the output. So let's say you double this, then it'll change it by psi plus alpha.
Yeah.
No?
Because basically doubling it, right, increases by psi % coming from the x and by alpha % coming from the other one, right? And so therefore you get an increase homogeneous of degree psi plus alpha. Sorry, which Matthew again are you?
Solomon.
Solomon, Matthew, yes. Okay. Okay. It's also linear in logarithms. That's exactly what I was saying before, right? So if you take the log of f, you get log of k plus psi times the log of x plus alpha times the log of a, and that's sort of the source of both of these two things. Another thing is that what's the slope of these isoquants? Well, that's how much production increases when we increase a divided by how much production increases when we increase x. And if you take the derivatives here, right, you get psi times k times x. Well, let me just do it on the board. So f sub a is k alpha x to the psi a to the alpha minus 1. And f sub x is k psi x to the psi minus 1 a to the alpha. If we divide this by this, k cancels out, all but one x cancels out. On the bottom, all but one a cancels out, and we get alpha x over psi a. And so this says that the marginal rate of transformation is proportional to x over a. That's saying that we're getting, for every unit of a, more production the greater x is and the smaller that a is, right? So the ratio of these determines their relative productivity. And therefore, if you have more of one, you want to have more of the other, more than if you had less of that one. So they're complements in production. These are related to one another all by this sort of logarithmic form that this takes, right? Okay. So another way to think about production is in terms of costs rather than in terms of production functions. And we usually classify costs into a few different categories. One is variable costs, and those are ones that increase sort of more or less continuously as you increase output. An example of this in our context would be time spent studying or time spent practicing sports, right? The better we want to be, the more we're going to have to do of both of those things in a pretty continuous way. A second category is lumpy, or what are called quasi-fixed costs. And these are ones that vary discontinuously with levels of output, but aren't absolutely necessary to produce any output. So they're necessary or useful to increase increase output in some range. So one example of that would be enrolling in a new class or taking up a new extracurricular activity. That's a lumpy cost. It's not fixed. You don't need it to do anything, but it's helpful. Or paying a tutor, buying new equipment. Fixed costs are ones that are necessary to produce anything at all, but can be avoided if you don't produce anything at all. So one example of that might be enrolling in school or starting a new club that you devote all your time to, right? And finally, there are what are called sunk costs, which are just fixed costs that have been undertaken in the past and that you can't undo now. And these shouldn't, in principle, affect your future decisions. So for example, if you already paid for tuition at a private school and you can't get your money back, that's now a sunk cost and shouldn't affect your future decisions. Okay. Now, costs can come from many different sources. One source of costs is money. And this is sort of like the most intuitive thing. So you have to buy things in order to go to school. You have to buy equipment. You have to buy textbooks, school supplies, etc. But then there's also opportunity costs of time or other resources. And this is a classic thing that you've already probably learned a lot about in economics. Time can be used for other purposes than studying. But this is also true for other scarce resources. So like your energy. If you use a lot of energy at school, you may be tired and not be able to use it in the rest of your life. Your willpower, if you work really hard studying and you focus a lot, you may not be able to focus a lot and endure hardship in your athletic endeavors. A third example are capital costs. So this has to do with depleting fixed resources that would otherwise have some future value. Sorry, this was last year's problem set. If you guys looked at this, asked you guys to explore this. But an example of this is reputation or physical appearance, health, etc. If you spend all your time studying, that may wear down, that may not give you so much time or actually wear down your health because you don't, because you're not eating enough, etc., etc. That has a cost to you in terms of the future value to you of that. Or if you are spending all your time studying, you might not have time to maintain your relationships with your friends and your family, and that might have a future value to you that you're deteriorating. Okay, so when do we use this cost way of thinking about things, and when do we use the production technology thing that we went through before? Well, costs are useful relative to technology because they help you think about how much you're going to produce, right? So it lets you think about the trade-off between going to college and other goals you might have in your life. It gives you one parsimonious number that summarizes all of this stuff. And in fact, when you thought about your own decisions in your life, this is probably how you think about stuff. You think, well, what's the cost of trying to, get into this job, get into this school, or what's the cost to me of having enough to go on this vacation, etc. Right? On the and this makes it particularly useful to help you interface with prices or with product markets. So for example, if we have a sense of what score you need to get into each school, that's a very easy thing to relate to the cost of achieving that particular score. It's also very useful when we want to aggregate across students. So if one student has a certain cost, another student has another cost, we can sort of put those all together to get a sense of where the market is going to be. Whereas if we think about things in terms of production technology, that can be very cumbersome because we're looking at such a detailed level at the exact way that everyone's producing everything, right? Okay. With fancier math, which we're not going to do today, it's also very useful to think about different things that you could be producing. So when I was thinking, you're trading off college versus other goals, costs are a very easy way to think about, well,